So number one wanted you to solve 3 tangent squared x minus 1 equals 0. And the thing to notice about this problem is that you only have one trig function. So the idea is that when you only have one trig function, you just solve it directly using regular algebra. So we'll go ahead and get rid of this minus 1 and times 3 by adding the 1 and dividing out the 3. Next, to get tangent by itself, you would have to take the square root, and this is what a lot of people forgot on the exam, despite me telling you numerous times. Whenever you take the square root to solve an equation, the result will be plus or minus. So we would have to figure out what angle has a tangent value of 1 over radical 3. So the reference angle that has a tangent value of 1 over radical 3 should be 30 degrees, or in other words, pi 6 radians. Now, since it's plus or minus, I know that this reference angle of pi 6 must be placed in all 4 quadrants. So there's a solution in the first quadrant, there's a solution in the second quadrant, there's a solution in the third quadrant, and there's a solution in the fourth quadrant. And doing a little bit of arithmetic should show everyone that these answers are not all symmetrical to each other. For instance, on top here, there are 2 pi thirds radians separating this answer from this answer, whereas there's only pi third radians separating this answer from that answer. So they are not all symmetrical, but I hope just by visual inspection we can all see that these 2 answers are symmetrical and these 2 answers are symmetrical. So this solution will have 2 statements. So what is the general solution? X equals, let's do the yellow, pi 6 plus pi k, because hopefully we can see that to go from yellow to yellow you only need to go 1 pi radians. And similarly, from purple to purple, you only need to go to move pi radians. Now, you can start either at any solution at the negative angle or the positive angle, but I'll just go ahead and use this angle here. So that's 5 pi 6 plus pi k. Some people chose to start at negative pi 6, and that's totally a-okay. That was number 1. Number 2 wanted you to solve cosine x sine x minus 2 cosine x equals 0. And the idea with this problem is that we have multiple trig functions, so that's, quote, harder. See, we have sines and cosines mixed together. But we should notice that we only have 2 terms. Here are those 2 pieces here, and they each have a cosine in common. So we can, use regular algebra. Let's factor out that cosine. And then we can apply the zero product property. Now, the right equation we should immediately recognize will not produce any solution because the range of sine or cosine is anything between 1 and negative 1. So this 2 here is way too big, so we're not going to have any valid solutions there. And then for the left equation, cosine of x equals 0, we should know that cosine is 0 at pi halves radians and 3 pi halves radians. So technically, we have 2 solutions, but they're symmetrical to each other, so we can condense it down to one statement. X equals, let's start here, pi halves plus, and we can see that we only need to traverse 1 pi radian to get to my next answer. Number 3. What does number 3 say? Number 3 says we want to solve cosine squared of 4x minus sine squared of 4x equals 0. I had a handful of students try to use Pythagorean identities to condense these guys down into one trig function. That's totally perfect. You can either use Pythagorean identity to transform the cosine squared into sine squares, or transform these sine squares into cosine squares. But the astute mathematician would notice that this is precisely the structure for the double angle formula for cosine. Recall that the double angle formula for cosine is cosine squared of stuff minus sine squared of stuff, which is precisely what we have. So the left-hand side is actually just simply cosine of 2 times this stuff, which in this case is 4x. So we're left with cosine of 8x equals 0. So although that angle is pretty big, notice that we only have one trig function, so we're going to just solve it like regular. So I'm going to put this on pause here, and I'm going to do a substitution for 8x. So I'm going to think cosine of theta equals 0, and then we'll go ahead and solve this. So if we recall from problem number 2, that this equation, cosine of theta equals 0, has 2 solutions, pi halves and 3 pi halves, but we can condense it down to one statement. So for this equation, we know that theta equals pi halves plus pi k. But our problem wasn't theta, our problem was 8x, so we're going to do that substitution. So we know that 8x equals pi halves plus pi k, and then to solve for x, you simply divide everything by 8. Some students made the mistake of not dividing this portion here. A lot of you guys did manage to divide the angle by 8, but you also forgot to divide the plus pi k or plus 2 pi k by whatever number. So the correct answer should have been pi 16ths plus pi 8ths k. Number 4. Number 4 says 2 cosine of 3x equals 1. And again, even though the angle is pretty wonky, we should recognize that there's only one trig function. So when there's only one trig function, you just use regular algebra. So to get the cosine by itself, we're going to divide both sides by 2. And then I'm going to think cosine of some angle, theta, equals 1/2. I'm not going to deal with the funky angle right now. So I know that in this particular equation, the reference angle is going to be, what is that, 60 degrees, pi thirds. And I know that cosine, since it's positive 1/2, I know cosine is positive in the first quadrant and in the fourth quadrant. So my two angles are, well, obviously pi thirds. And I'm going to stick with the positive angle here. And that second angle is going to be 5 pi thirds. And I hope it's very clear to everyone that these angles are not symmetrical to each other. So we're going to have two statements. The yellow answer plus 2 pi k, and then the purple answer plus 2 pi k. So we have theta equals pi thirds plus 2 pi k, and 5 pi thirds plus 2 pi k. But again, our original question wasn't theta, our original question was 3x, so I need to do that substitution. So we're going to say 3x, not k, 3x equals pi thirds plus 2 pi k, and then 3x equals 5 pi thirds plus 2 pi k. And I hope it's very clear to everyone what we need to do to solve for x. We'll just divide everything by 3. So that gives us our grand final answer of x equals pi ninths plus 2 pi thirds k, and 5 pi ninths plus 2 pi thirds k, where k is some integer. What are we on? Number 5? Number 5 said, for cosine squares minus 4 cosine x plus 1 equals 0. So the thing that we needed to notice here is we have multiple trig functions, but they're the same at least. They're both cosine, so that makes it slightly easier for us. We should have noticed that there are 3 terms. We started with a square, So here's cosine squared. Then we're left with a linear cosine, just a single cosine, and a constant. This is a quadratic. Even though it doesn't look like it, uses trig, it is technically a quadratic. So you can factor it or solve it like a regular quadratic. And then this just took knowledge of factoring. So you needed to know how to factor 4 times something squared minus 4 times something plus 1. That's what you needed to be able to do. So if you factored this correctly, you would have ended up with 2 cosine x minus 1 times 2 cosine x minus 1. Notice how they're the same factor, so you really don't need to solve both of them because both of them will yield the same result. So in either equation, applying the zero product property, you're asked to solve 2 cosine x minus 1 equals 0, which means cosine x equals 1/2, which I believe we've already solved in number 4. So let's refresh our memories. The reference angle here, what angle has a cosine value of 1/2? That's going to be 60 degrees, or in other words, pi third radians. And this says cosine needs to be positive. So I know that cosine is positive in the first and in the fourth quadrant, which means my two actual angles are pi thirds. And you could have used the negative angle. I'll go ahead and show the positive angle. That second angle is 5 pi thirds. And notice how they are not symmetrical to each other. The yellow answer and the purple answer are not symmetrical, so you're going to need two separate statements. For the yellow answer, you need to go all the way around in a full circle, 2 pi k. Same thing with the purple answer, all the way around in the circle, 2 pi k. So that means our answer should be pi thirds plus 2 pi k, or 5 pi thirds plus 2 pi k, where k is just some integer. Number 6 says solve 1 minus 2 sine x equals cosine of 2x. So here's sort of like the, anything bad that can happen did happen. Number 1, we have multiple trig functions. Number 2, they are different. This is sine, this is cosine. And number 3, the angles are different. This is an x and this is a 2x. So your job to make this a, quote, easy problem is to get all the trig functions to be the same and or get all the angles to be the same. Now, I hope it doesn't shock anyone, or I hope it's noticeable that this right here, we have identities to take care of it. This is precisely the double angle formula for cosine. Now, the double angle formula for cosine has 3 variations. Since our other trig function is sine, it would make sense, it would be smartest to use the trig variation that has sines in it. So I'm going to use the double angle formula for cosine that says cosine of 2x equals 1 minus 2 sine squared x. So now at the very least, they're all in terms of sine, they all have the same angle of x, and we notice, or should notice, that we have a sine squared and a regular sine. So I'm going to guess, it's not 100% confirmed, but we have a good feeling that it's probably going to be a quadratic. So to solve a quadratic, we want to get all the terms onto one side. We want the other side to be 0. So let's go ahead and subtract the 1 and add the 2 sine squared. And if we do that, we're going to get 2 sine squared x minus 2 sine of x, and then the 1's will cancel out. And lo and behold, we can solve by factoring because it is a quadratic. So they have a 2 sine x in common, left with sine x minus 1. So then, according to the zero product property, once you divide up the 2, you get sine of x equals 0, and then sine of x equals minus 1 equals 0. Let's show our work here, which of course means sine of x equals 1. So for the left equation, actually we're going to put all answers, because I recognize 0 and 1 are special. We'll put all of our answers on one coordinate system. Let's do the left equation, sine of x equals 0. Knowing the unit circle, we should know that sine is 0 at 0 radians and pi radians. And we should know that sine is 1, to solve the right equation, at pi halves. So we have 3 answers. this answer here, and this answer here. Visually, they are not all symmetrical to each other, but I hope everyone can see that the yellow and the orange answers are symmetrical. They are actually split by 1 pi. So we can actually write or condense the entire solution to 2 statements. So let's do the yellow one. So you get x equals, start at any answer. I'll start at 0 plus, and we have to go pi k to get to your next solution, right? If you start at 0 here, you would have to move 1 full pi to reach the next answer, then another pi to reach the next answer, so on and so forth. Not theta, 0. Now, anytime you have a 0 plus, that's sort of redundant. You don't need to write 0 plus, so I'm just going to write pi k. Now, the purple answer, we start at pi halves radians, and then since it's not symmetrical with anything, you have to go a full circle, 2 pi k, to reach your next answer. That should have been the solution for number, whatever this is, number 6, I think, yeah. Number 7 asks you to solve sine of 2x times cosine of x minus cosine of 2x sine of x equaling radical 3 over 2. Right. Now, I had a couple of students recognize you had double angles here, and they used the double angle formula. That is a-okay. That is perfectly fine. But you should have noticed that this had a particular structure. Notice it used the same 2 angles, 2 x's and a regular x. Also notice the trig functions have a set pattern. Sine of the yellow, cosine of the purple, cosine of the yellow, sine of the purple. Or in other words, sine of the first angle, cosine of the second, minus cosine of the first angle, sine of the second. This is precisely the structure for the sine of a sum identity. So you could have used the double angle formula, but the astute mathematician would have recognized that this entire thing is just sine of a difference. Right? This is a sums and difference problem. So we should have recognized that this was sine of 2x minus x. Oh, I shouldn't use an equal sign here. All of this here is sine of 2x minus x, which equals rad 3 over 2, which of course is just a simple sine x equals rad 3 over 2. That's it. That's all you really need to do in terms of rewriting or manipulating this equation, and the rest is just solving it. I hope this is a relatively easy equation to solve, right? A reference angle. What angle has a sine value of rad 3 over 2 is 60 degrees, pi third radians. And I know that this says sine is positive, and we know that sine is positive in the first and the second quadrant. So that means our angle is pi thirds, and our second angle is 2 pi thirds. These two answers are not symmetrical to each other, so you'd have to go a full circle, 2 pi k, to reach your next solution. So our entire general solution is x equals pi thirds plus 2 pi k, or 2 pi thirds plus 2 pi k. Number 8 asked you to solve sine of 3x minus sine of 6x equals 0. And this one here had lots of different ways to solve it. So if you took a different path to solve this equation, your final general solution may look differently than mine, and that's a-okay. I went through all possibilities, and if it was correct, I marked it as correct. I give you credit. I'm gonna just, in my personal opinion, go to the path of least resistance. So what I notice is that we have a sign minus a sign, and you can go ahead and use the product to sums and sums to products identity. But then there's some adding and subtracting and dividing by 2. It gives you fractional angles. So when I first did that route, the answer, it was correct, came out a little bit messy. The other thing I notice is that this angle here is exactly half as much as this angle. Or in other words, 6x is double of 3x. So maybe, I'm not sure, but maybe the double angle formula for sine applied to this guy might be more convenient. This is what I mean. You should recognize that sine of 6x is the same thing as sine of 2 times 3x. Now, written that way, you can apply the double angle formula for this term here. So that gives us minus 2 sine of 3x cosine of 3x. Now that looks like it makes things more difficult, more complicated, but notice we have two terms here, and they both contain a sine of 3x. So we can just do straight up factoring. So that's why when I did this the second time, I found that this to be slightly easier and cleaner. But, you know, using the sums to products or products to sums is not wrong at all. So we're going to factor out a sine of 3x. That gives us a 1 minus 2 cosine of 3x. And then we can apply the zero product property. Sine of 3x equals 0. 1 minus 2 cosine of 3x equals 0, which means this is what? Cosine of 3x equals 1/2. So, I guess I'll just show my full work. To solve the left equation, where is sine 0? We should recognize sine is 0 at 0 and pi. They're symmetrical by 1 pi. So this angle here, 3x, is equal to 0 plus pi k. And as I said before, and I think it was problem number 7, anytime you have 0 plus something, you don't really need that 0 there. So the answer for this part, at least, is pi k. And then clearly divide everything by 3, so x equals pi thirds plus, pi thirds k, that's it. To solve this guy here, we should know that the reference angle, or what angle has a cosine value of 1/2, is 60 degrees, pi thirds. Cosine is positive in the first and the fourth quadrant. So that tells you that your two answers are pi thirds. And I'll use the positive 5 pi thirds. So typically, your angle, which in this case is 3x, we get 3x equals pi thirds. And you have to go full circle because these two answers are not symmetrical to each other. 2 pi k, and you get 3x equals 5 pi thirds plus 2 pi k. And clearly, you'd have to divide everything by 3. To get your final solution. So let's put everything together. So you get x equals, I'll put this guy down, pi thirds k. Or this answer here, pi ninths plus 2 pi thirds k. Or this answer here, 5 pi ninths plus 2 pi k. 2 pi thirds k, where k is an integer. So that was the solution for number 8. Number 9 asked you to solve cosine of 4x plus cosine of 2x equaling a cosine of x. So lots of things going on here. One thing I noticed a handful of students trying to do is they noticed that you had even angles here, 4x and 2x's. So they try to use the double angle formula for cosine repeatedly, and I think theoretically that is possible, but it's going to make such an ugly, messy problem. One thing to also note is that all the angles sort of have a pattern, 4x, 2x, and 1x. We should notice that this x here is exactly the average of the difference of these two angles here. Now, why am I thinking of averaging of the differences? Well, one of the more important identities in trig are the product to sums and sums to products. And when you use those identities, you're always taking the averages of either the sum or the difference. So for the product to sums and sums to products, we do have a cosine of a cosine formula, and that's exactly what we're going to apply here. So on the left-hand side, we're just going to apply the identity for cosine stuff plus cosine other stuff. So on the left-hand side, according to the identity, cosine of 4x plus cosine of 2x equals 2 cosine of, add them together, divide by 2, times cosine, subtract them, divide by 2. Now again, this makes it look very, very messy, but notice what it does. It transforms the problem into a multiplication problem. Basically, it quasi-factors things, and things are always easier to solve when it's factored. So 4x plus 2x divided by 3 is 3x. And then this is that single x that we wanted. But of course, to solve by factoring, the equation needs to equal 0. So we'll go ahead and subtract the cosine x over. And now we should notice this is one giant piece, this is another piece, and they both share a cosine x. So we can factor out that cosine x. So we can apply the zero product property. So we get cosine x equals 0, 2 cosine of 3x minus 1 equals 0. So, use algebra. Cosine of 3x equals 1/2. So the left equation, where's cosine 0? Cosine is 0 at pi halves and 3 pi halves. Notice they're symmetrical by 1 pi. Where is cosine 1/2? To solve the right equation, that angle should be pi thirds, 60 degrees. Cosine is positive in the first and the fourth quadrant. And I hope everyone can see that we have two answers. Theta 1 is pi thirds, and I'll use the positive angle. Theta 2 is 5 pi thirds. So to answer the left equation, we have x equals, start at pi halves, and you only have to go 1 pi to reach your next solution. For the right equation, we have a little bit of extra algebra to do. So we know that the answer should be pi thirds plus 2 pi k, or 5 pi thirds plus 2 pi k, because these two answers are not symmetrical to each other, but we didn't have a regular theta, we had 3 x's. So of course, to solve for x, you would have to divide everything by 3. So let's put our general solution over here. So we have this part here. Then to write this answer, we have pi ninths plus 2 pi thirds k and 5 pi ninths plus 2 pi thirds k. That should have been the general solution for number 9. Last but not least, number 10 asks you to solve 2 sine squared x minus cosine x equals 1. I think this is, ironically, being the last one, probably the more straightforward one. We have two different trig functions, sines and cosines, but we recognize one of them as being squared. That almost always calls for Pythagorean identity, and that's exactly what you had to do here. So we do a Pythagorean identity substitution. So we should know that sine squared x is 1 minus cosine squared x. And then just do algebra. 2 minus 2 cosine squared x minus cosine of x. Let's go ahead and subtract this one over since we're here anyway. I also like the squared term to be positive. Let's combine like terms. So what I'm going to do here is I'm just going to divide everything by -1 to make the cosine squared term positive. Makes factoring easier because this is a quadratic. You have cosine squares plus cosines and then a constant. So it factors into 2 cosine x. Cosine x, the middle needs to be a positive 1, so we got a plus 1 on the right, minus 1 on the left. Zero product property says that the first factor equals 0, and the second factor equals 0. So doing a bit of algebra gives us cosine x equals 1/2 and cosine x equals -1. Let's actually put all these answers together in one coordinate system just to save some time. Let's solve the left equation. Now, if you've been following along throughout the whole solutions videos, we have solved this equation like 3 or 4 times now, so it should be automatic. What angle has a cosine value of 1/2? The answer is 60 degrees, or pi-thirds radians, and we should know that cosine is positive in the first and the fourth quadrant. Let's solve this guy here. Where's cosine -1? Well, that's a quadrantal angle at pi. The interesting thing here is typically, technically we have 3 answers, the yellow, the purple, and the orange. But in this particular instance, they're all symmetrical because we can clearly see that there are 2 pi-thirds in this region, 2 pi-thirds angles, right? If this is pi-thirds, this is 2 pi-thirds. Well, knowing that the whole guy, the semicircle, is 1 full pi, this piece here must be 1 pi-thirds less than 1 full pi, or in other words, 2 pi-thirds. And then, like in the same logic, this has to be 2 pi-thirds. So all 3 answers are actually symmetrical. So you didn't need to write them as 3 separate statements. Now, if you did write them as 3 separate statements, I gave you full credit for it. But the astute mathematician should observe we can be efficient with our answers as 1 statement. If you wrote it as 1 statement, I gave you a little bit of extra credit. So to write it as 1 single statement, start at any of the answers, the yellow, purple, orange, it doesn't really matter. I think starting at the yellow is easiest, and we can clearly see that we don't need to travel 1 full pi or 2 full pies. You only need to travel 2 pi-thirds to get to your next solution. So that should have been the solution, the general solution for number 10.